Hello everyone, my name is Shravan and my teammates are Aravind, Derek, Karan and Mike. We are Team 10 and our project is a mobile manipulator for object relocation. We have chosen the Fetch robot as our mobile manipulator platform and implemented the concepts learned in the robodynamics course.
Robotic systems to automate industrial activities are not a new business strategy. Industrial-specific robotic systems in the past have been regulated to manipulator arms in a fixed static position with limited range for activities. This all changed in recent years with Amazon's acquisition of Kiva in 2009, which is now called Amazon Robotics. Kiva's system was basically a mobile robotic base that would pick up entire shelving units and move them from one location to another, in which a human could pick out the correct product. Today, most robotic companies looking to design the next generation warehouse robot are looking to create a system in which a robot is a mobile base with a manipulator arm attached. To dig into this problem a little bit more, we decided to use Fetch Robot from Fetch Robotics. Fetch consists of two separate robots, Fetch, which is the torso, and Freight, which is the base.
When creating the drive controller for the base of the robot, the relevant messages we used were the odometry and twist messages. The odometry message is published by the base and includes a pose which consists of the robot's X, Y, and Z position, as well as a quaternion representation of its orientation. The quaternion can then be processed to give the orientation in Euler angles. The base also subscribes to a twist message. The twist message is composed of a linear and angular array of 3 vectors each. The linear X vector is used to command the robot's forward velocity in meters per second, while the angular Z vector commands the rotation of the base about its center in radians per second. The other vectors are ignored. For our project, we created a point-to-point control algorithm for the base using the messages previously mentioned. The algorithm takes in an X, Y position as a target location to drive to. It then calculates the angular error from its current heading to the target and rotates by that amount. The desired max speed is taken in as an argument when rotating, but the base will slow its rotation as it begins to face the target to minimize overshoot. The robot will then drive forward to the target. Since there is a small error associated with the rotation, when driving forward, the robot will apply a rotational correction based on the angular error to the target. A final heading can also be specified to leave the robot in a desired orientation once it has arrived at its target location. This point-to-point driving can then form the basis for future more complex navigation algorithms.
The Fetch robot uses 2 sensors for object recognition and robot localization. There is an RGB depth camera in the robot head for short-range object recognition and laser rangefinder in the base for robot localization. We first use the laser rangefinder to map the local simulated environment. To map the environment, you must first drive Fetch around manually to build a map based on the laser rangefinder's output relative to the robot base. The gridded figure in the middle is the robot output of ROS visualization, or RViz, while driving around the environment. Gray represents the known areas, while black represents the unknown and no-go zone. Once the robot is driven around the environment, a map is produced like the one on the right-hand side. This map can then be used to avoid known obstacles in the static local environment.
The Fetch robot arm has 7 degrees of freedom. Here, the torso movement is controlled separately. The slide shows the overview of the task required to solve arm trajectory planning. First, we begin by deriving the DH parameters for the robot arm. Then we use quintic polynomial for trajectory control of the joint space. We have used track IK which is an open source inverse kinematics solver to obtain inverse kinematics of the manipulator. Finally, we derived the dynamics for the robot arm in the MATLAB. As shown in the slide, we derived DH parameters for the robot's arm by assigning the frames for each joint according to the DH convention. We used 3 dummy frames and calculated link transformations from the base link to the gripper link. Here base link frame is at the midpoint of the line joining the centers of the two wheels. We derived respective dimensions for the robot links mentioned in this figure from the URDF file of the robot. We noticed that fetch robot frame convention wasn't according to the DH convention frame. So we changed URDF to simply follow DH convention, which helped us to compare our MATLAB results with the raw simulation.
In this video, we can see the arm being controlled in joint space. We have used TrackIK solver to solve for inverse kinematics that transforms the final end effector position to a feasible joint space values. TrackIK is a ROS compatible software that solves for IK given the start and end point of a kinematic chain. Once we obtain the joint space values, we generate trajectories that follows quintic splines for each joint, which will allow the arm to move to the required end effector position. To enable feasible gripping position, the final joint of the arm is kept at a fixed angle with respect to the base frame of the robot. As you can see, the arm is able to move from one given end effector position to another. In our algorithm, we have created separate modules for different aspects of controlling the arm. For instance, we have separate modules that help us perform IK, trajectory planning, trajectory following, and gripper action. We have created a finite state machine for our task, which integrates these modules, helping us to perform different actions with the arm. This is clearly evident from the video, where we can see the gripper module executing only after the trajectory follow module is completed.
For the ease of Jacobian calculation, we locked one of the joints that connects the gripper and found the forward kinematics with respect to position and velocity. We obtained the Jacobian and proceeded with the Lagrangian method to obtain the joint torque equations. We assumed the mass of the links of the manipulator to be of point mass while calculating the Lagrangian, because our intention was to obtain the dynamic model for simulation purposes. Our final report will include gripping of an actual object and the integration of the arm and the base of the robot to perform a pick-and-place action in sync. This will be visualized on Gazebo. We sincerely thank Professor Fisher and fellow classmates for valuable inputs and their guidance throughout this course. Thank you.